Hello. Shivay and I will be talking about WebAssembly-based AI as a service on the edge with Kubernetes, and particularly we want to talk about using WASM on the edge. We'll particularly talk about machine learning applications, which are pretty compute intensive. Though a lot of the ideas we talk about can be applied to other kinds of applications, we want to talk more about machine learning applications on the edge with WebAssembly, and in general about how you can run WebAssembly on the edge. Now, if you don't know a lot about WebAssembly, we'll also do a quick intro to WebAssembly. Yeah. But hello, I'm Rishit. I'm a student at the University of Toronto, and I've been contributing to Kubernetes for quite some while.
And I'm Shivay. I'm a contributor and meshmate at Layer 5, which is service mesh community. And I've been a contributor to Kubernetes and a lot of the cloud native projects for about 2 years.
So I want to start out with a quick introduction to WebAssembly, and we won't go very much deep in it. This is a misnomer, but a very famous meme. I like to start talking about WebAssembly by. And you might have seen this meme somewhere. If not, we start by saying that WebAssembly is neither web nor assembly. And by neither web nor assembly, what we mean is you do not write code in assembly, and you do not have to run it on the web, though you can run it on the web too. Okay, so let's start by talking about WebAssembly. So very simply, it's a binary instruction format for a virtual machine, changes to binary instruction format for a stacked virtual machine, and also WebAssembly is designed as a compilation target. What this means is you can have your code written in C++, Python, Java, Rust, whatever you like, and have it compiled down to WebAssembly. And then you run the WebAssembly, no longer the code. You wrote in any language you write. So that is what WebAssembly is. It is a compilation target. And why would you want to have this compilation target when you can just have a C++ compiler do it for you? Well, we'll talk a bit more about that soon. But so WebAssembly is efficient and fast. You can have your code run at near native speed with WebAssembly, which is what we also want for edge applications. So we want to talk a bit more about this. But you can have your code run at near native speed with WebAssembly. It's also open source. It's open and debuggable. As well as you can run it on non-web platforms. So WebAssembly started out as a way to just run it on the web. That's how it started out. But today you can run WebAssembly outside web platforms, on microcontrollers, on your phone, wherever you want. And we also want to talk about some of the challenges while running WebAssembly outside the web and how you can solve them. So we also want to talk a bit more about this, but you can also run it on non-web platforms. It's also built with the open web platform in mind. And what I finally want to talk about when talking about WebAssembly is it's safe. So the WebAssembly memory model, so if you see the WebAssembly memory model, no program can break it. Now that of course doesn't guarantee that a program can't corrupt its own memory and do that. That of course doesn't, the WebAssembly memory model doesn't guarantee that, but the WebAssembly memory model does guarantee that no program can break it. So that is pretty interesting with what you can do with WebAssembly.
So yeah, just to kind of summarize on what we have basically covered so far is that what WebAssembly is basically a high-performant independent bytecode. So you're taking your programs that you have written in your programming languages, whether it's like your functional programming languages or even your scripting programming languages, and then you're basically using WebAssembly as your bytecode or as your compilation target. And again, those are because of the fact that, as Rishit covered some of the benefits of using WebAssembly because of its small size and small footprint, its quick load times, and that will also be explaining more and how it kind of is used in edge-based applications. That's why it's a very popular target to not use actually your functions written in popular programming languages like Python or JavaScript, but instead to compile it to this WASM bytecode and actually use it. And as you mentioned, that it's a polyglot language because it supports multiple programming languages. And since it's it's essentially a bytecode, that means it runs at near native speeds, and that's why it's very performant as well. And of course, that's what we have covered, that the code executables run directly and interact directly with your native hardware, and that's how you can use it with edge-based devices as well, and that we'll be covering some of those applications in our demo as well. But yeah, that's one of the major benefits, and that's why we'll see how it can be used in applications such as machine learning, where you need a lot of compute power. But of course, if you are working with edge devices, the most biggest use case that you find is that your resource constant because of the low power that you get with edge devices. So how can you make the most out of those low powered devices and still be able to run more compute intensive applications such as machine learning on those edge devices? So that's where basically WebAssembly comes in the picture.
So while talking about the representation that WebAssembly has, so it's essentially a representation, right? So okay, before I move any forward with the representation, I also want to say that another novelty or another benefit you get with WebAssembly is the size of it, and you can try doing an experiment, and we'll also show some benchmarks for this, the experiments we have done. But you can try doing an experiment with having a container running some process, and try seeing the size of that container or the startup time of that container, and have the same being done with WebAssembly. And you can also have WebAssembly modules as containers. There's a very popular tool called WASM to OCI, or you can also have other ways to do it. But if you see the startup time of WebAssembly, you can get almost 100 times speed up with in comparison to normal containers. Now that's of course not every time 100 times speed up, but some experiments do show that you can get a lot better startup times. Also, talking about the container sizes, if you specifically want to deploy containers, how small can you get Linux containers? Probably you'll use something like Alpine and do some kind of optimizations and all of that, and get your application to be as small as probably 15 MB, 20 MB, probably even smaller. Whereas some of the WebAssembly examples will show, because it has no guest OS, so you can have WebAssembly containers as small as 6 MBs, 7 MBs, or go even smaller with your whole application contained in it. So the WebAssembly representation itself is compact, modular, efficient. But some of the parts which I haven't covered earlier, which I want to talk about, is it's pretty portable, and you can run WebAssembly wherever you want. It's also the WebAssembly representation is pretty portable.
So this is where we kind of bring the application of WebAssembly into the edge, because so far we were giving a primer on what exactly is WebAssembly. So that's where we'll introduce the WasmEdge runtime. It's so basically what's WasmEdge? WasmEdge is it's an open source program project that is currently incubating under the CNCF, that's the Cloud Native Computing Foundation, and it's a WebAssembly runtime that allows you to run WebAssembly modules on the edge, and it's primarily used for running like machine learning inference, being able to run smart contracts, so you can use it for blockchain based applications, and even you can run the actual WasmEdge runtime on platforms such as your Android devices, or even on Raspberry Pis, right? So those are some of the applications where you can actually run this runtime, and it uses ahead of time compilation, so it's very quick in being able to do the inference for you. So we are going to be focusing on this WasmEdge runtime for some of the demos that we'll be showing today.
Okay, that's great. You have a way to run WASM on the edge, but what we talked about was WASM started out for the web. How do you go beyond the web? And there are a ton of problems when you go beyond the web. I want to start by focusing on some of these problems. So first off, what we want is a fast, scalable, secure way to run the same code across all machines. This is what we want, pretty simple for our use case. And I want to stress on the part that I want the same code to run on all machines. This code should also be safe and portable. And well, the WebAssembly memory model handles that. And but by safe and portable, so some part of it is handled by the WebAssembly memory model, but by safe and portable, I also mean that users and programs can do what they have the right to do, and they do not create problems for other users and programs. This seems pretty simple because this is what the kernel does for you. But if you want to run the same code across all machines outside the web, what you need to be able to do is have standard platform-independent methods to declare and apply. So wait, what do we want to declare and apply? So these are essentially system calls. So if you take a language something like C++ and or any other language, these rely on standards like POSIX, and with the compiler and these standards, the compiler makes a binary out of it, and then the binary can run across a host of or a lot of OSes and processors. So I want to be able to do that too, but I want to be able to do that for a lot of different programming languages, and I want to still be able to run the same code across all machines. I also want binary compatibility. So for all of this, we introduce WASI, WebAssembly System Interface. And I want to show a very interesting tweets by Solomon, who is the founder of Docker. And in 2019, he tweeted, if WASM plus WASI existed in 2008, we wouldn't have needed to create Docker. So I want to start by introducing WASI and how WASI comes into the place. So I'll start by talking about system interface, and I want to give some context around system interface, which will motivate the use of WASI. So see the line, C gives you direct access to system resources, which is of course false because it's far too important for stability and security. What happens is, this is a nice diagram by the WASI team. So what happens is, your applications go to the kernel, and the kernel will decide what application should access what resources, or if it wants to access some file, if it wants to make some changes to a file, it will go to the kernel. Pretty simple, nothing new here. What WASI introduces here is have the ability to do this system call, this system interface and all these system calls, which were earlier being handled by the kernel. Now you want to run it across all devices. So what you do is have standard libraries implemented with WASI, and these WASI libraries allow you to do system calls across multiple languages. You write some code in Rust and use WASI to do the system call, or you write some code in C, use WASI to do the system call, compile it down to WASM, and then run it wherever you want. So instead of doing the system calls with some C-specific library, you would probably have some C-specific way of doing a system call and some Rust-specific way of doing a system call over here. You just use WASI to do these system calls. Okay, so that allows us to run WASM outside the web, because now you have a platform-independent way of doing system calls. And this is also language agnostic. Use it in any language you want. So okay, now I can run WASM outside the web, but before going on to a demo and showing how WASM runs outside the web, what I also want to do is talk a bit about multi-threading. And WASM doesn't right now support multi-threading. There is a proposal for WASM threads, and I particularly wanted to talk about this because your edge applications might have a lot of use for multi-threading in WASM. And there are, of course, strategies you can employ to still run your multi-threaded applications. We will see this in the demo. But there is also the threads proposal, the WASM threads proposal, which allows you to do multi-threading in WASM. And the way this works is particularly makes the use of atomic instructions, and you might be familiar with web workers. So I won't go in detail into the WASM threads proposal because we are already running out of time. But there are a couple of changes on how you would do this. So one particular use case of WASM you might have already thought of is probably have your web application or some other application do some of the processes in WASM, probably have some compute intensive workload running in WASM, and have rest of your application written in some other language. So you also need changes to bindgen and how the compilation is done to support multi-threading. The way the memory is handled will also be different. But there is a WASM threads proposal that allows you to do this. Okay, with that, I want to take a look at some demos to do what we talked about. In particular, we'll be taking a look at 3 demos. And to set up context for the first demo we have, I have trained a MobileNet machine learning model. I've converted it to TensorFlow Lite. So TensorFlow is a popular open source library which I contribute a lot to as well. And it allows you to run machine learning models on edge. TensorFlow Lite is one particular library that allows you to run machine learning models on edge. So you can just use TensorFlow Lite on the edge as well, and that's pretty nice. That's pretty neat. But we'll show some benchmarks. But right now I have a machine learning model, converted it to TensorFlow Lite, so it is optimized to run on the edge. It's not a huge model. And then I want to run it with WASM. This is one of the demos we'll be seeing. And I'll show the benchmarks for the exact demos in some time as well. The other demo I want to be able to show is being able to use multi-threading capabilities. So you probably have already your code read. By the way, you can replace machine learning with any compute-intensive process. This is an example we take because we have been working in the machine learning field for long. So you can take any open source library which probably uses multi-threading like Tract to run machine learning inference and still run it with WASM. The third demo we'll be seeing quickly is WASI, which is a gateway interface. So WebAssembly does not have nice ways to write web servers, which introduces the use of WASI, which is essentially a re-implementation of CGI for WASM. We'll be seeing how you can put it into an end-to-end application, while we'll also see how you can make a web server out of the WebAssembly modules. So let's quickly take a look at some of these demos. And the first thing I'll do is, I have a lot of other things if anyone wants to try out, but the first thing we'll do is I have a Rust MobileNet demo, and it's probably not visible, the file directory, but you don't need to see it. So I have the MobileNet demo, and what this has is some Rust code to run my machine learning model. First off, what I want to do is do a build, and what I put in as a target is WASM32 minus WASI. So I tell it that I want to be able to I want to run it on WASM. And if I show you the Rust code I'm using, it's essentially just loading the model, performing an inference with the machine learning model, and printing out what did it get. So it's a pretty simple model, nothing very fancy over here. And it's some Rust code to do this. I'll compile it while telling it to use WASI, the system calls from WASI. So that's what I'll be doing. So let's start by doing that. And I'll do a cargo build for this. So I'll do this. So the cargo build will be pretty fast because I ran it just before the demo, so the builds are fast. So I mean, it's not building anything new. It's just seeing that everything has been built. So I ran this just before the talk, so we get done faster. What I want to do now is use WasmEdge to be able to run this Rust app locally. And I'm showing an example of running this locally. Of course, you can take it to the edge with WasmEdge, which is the idea we talked about. So if I first do an ls on target wasm32 minus wasi release. So I see that I have multiple files over here. One is called classify.wasm, which is the WebAssembly module I have. I'll be running this WebAssembly module whenever I need to run WebAssembly. The .wasm file or the WebAssembly module is what I'll be running. And if I also do, so this is an end-to-end proper application, a proper machine learning application. And if I also do an ls minus l over here, you see it's actually 6 MB. That's your whole application. You run this, your container will be 6 MB huge if you convert this to a container. And this is a proper mobile net model you can run on the edge. Okay, so having given you some background, let's go back to the directory I want. And with that, I want to now be able to run this with WasmEdge. So WasmEdge is, as we talked about, it's a WASM runtime. You can use any runtime. WasmEdge is optimized for edge devices. So let's do that. Let's run the .wasm file we have. Let's pass it an image. So I have multiple images over here. One is, okay. So I'll just download this image actually. So I have two images for my machine learning model, and these are just representative because your applications will most certainly differ. This is a fish called tench, a particular class of fish, and my model is trained to identify all kinds of objects, while this is a person in a military uniform. So let's try putting in the first one, and it does say it's a tench, and we can also try putting in the second one. But you essentially get the idea. We are using WasmEdge to run that WebAssembly, and this tells me it's a military uniform, which is also what this is. But what I wanted to show is not the output, but the idea of using WASM, running it with WasmEdge. So okay, so that is a WebAssembly module we just ran and now I'll go to the second demo we talked about. So what we want to do right now is use some multi-threaded library which you might already be using for your machine learning stuff or whatever you want to do with WASM and power it up. So I want to be able to do this as well. And okay, right now what we have over here is same demo, the same model, but now I have some other library to do it, which probably uses multi-threading. This one does. So this is also some Rust code, and why is all of this commented? Interesting. Oh, okay. I have the same code written twice. One is commented. That's what happens when you write it in the morning. But anyways, so I'm using tract, which is a way to do TensorFlow and Onyx inference on the in Rust, and tract is multi-threaded. Without using WASM threads proposal, you probably won't be able to do this. But I'm employing some strategies on how the image is loaded to no longer use multi-threading. And which is exactly what I'm doing in this demo. And I can run this with WasmEdge as well. So let's open up the commands. I'll again start out by building it for wasm32 minus WASI, which is what we want to use. So it has finished the build. And now I can use WasmEdge, WasmTime, whatever I want to be able to run this model. I'll start by showing so WasmTime is another runtime. So I just wanted to show that with a WebAssembly module, you are not limited or tied to container runtimes or what machines you can run it on. You can take the exact same .wasm, run it on a microprocessor. I can also run it with WasmTime. No use of I can if I didn't want to use WasmEdge at all. I can put this up on I can run this on a server. I can run it on a edge device. Of course, our use cases for this talk are more focused on edge, but I can also use WasmTime, which is pretty useful for servers. This tells me the output is 2, and 2 over here just means I haven't written the code to parse it from the image map because this is 1,000 labels. So it tells me what number this is, and 2 just means you're a tench. So that did work, but I can also use WasmEdge to run it. And the code to do it would actually look pretty similar. I would first mount the directory, and instead of using the runtime I want, I can just use WasmEdge, and then I can use WasmEdge to run it on an edge device.
Yeah, so as you saw that we pretty much used like 2 different types of runtimes, and since you're slightly running out of time, we'll probably skip the WASI demo right now, and we can probably share that after this link, but we'll probably proceed back to the slides. And but the idea is that by default WebAssembly does not allow you to create your own web servers, but with the WASI proposal it allows you to actually create web servers where you can have an restful endpoint. And so the example that we want to showcase was like a predict endpoint where you'll see the inference taking place on side of a deployed web server that we were using with the code space, GitHub code space. But coming to the probably the last part of our presentation, and that's primarily that if you are, like, let's say, willing to run your WebAssembly AI service, right? Because especially if you're using edge devices, a lot of times you'll probably use something like a function as a service. But before that, we'll also just like to talk a bit more about how WASM can be used with Kubernetes. So again, the idea with Kubernetes is that you can run multiple containers, and Kubernetes is a container orchestration platform. So the idea is that, as we discussed, that your standard Linux containers can be extremely heavy, right? And they have a very long boot up time. Now, with that in mind, what we want especially for edge applications is containers that have a very small blueprint in terms of the memory, and also they have very fast runtimes, right? They can start off very quickly. So that's where we are going to be also using Kubernetes to manage WebAssembly based containers. Again, the idea is that you're not replacing your containers with the Linux containers with WebAssembly, but what we are actually introducing is that how you can run your WebAssembly containers alongside your Linux-based containers or with Docker containers, and run them inside of a Kubernetes-based system. So again, that's what the goal is, because WebAssembly in itself cannot do a lot because the way the sandbox model or the security sandbox model of a WebAssembly works is that you need to introduce things like WASI to introduce networking or file handling capabilities. So what you can do is that you can probably run all your compute heavy tasks inside of your WebAssembly container while still use some of the Linux containers, your standard Linux containers, to handle your other processes. So this is what we propose inside of a Kubernetes based cluster if you are running it alongside inside of a Kubernetes cluster. But we'll also talk a bit more about serverless computing. So you probably might have come across the term serverless in some time of your career. And of course, today serverless functions are very popular because you don't need dedicated servers to run your backend code. And what serverless enables you to do is have them whenever you actually have to make a call, you just need to spin up your serverless function at that point of time. So it's also very scalable in comparison to your servers. So the idea is that with WebAssembly, since it's a very small runtime and it's very highly performant, so you don't need to use your typical functions that might be written in Python or JavaScript. Instead, you could have your serverless functions written in WebAssembly and then execute those. And these are much faster than your typical functions that you might be writing in, let's say, AWS Lambda, or if you're using some other functions. So we actually see the use of WebAssembly based functions in a lot of popular technologies as well. So Vercel recently introduced edge functions, and then Netlify also has edge functions that are basically using WebAssembly in order to use them. And again, one of the better benefits is that since these edge functions are running across multiple CDNs, so the spin up time for these is very quick, and of course you get the performance and the portability as well with WebAssembly, because of the fact that since you just compile your function as a WebAssembly bytecode, it can run across multiple platforms. So you don't even have to be platform dependent in terms of like the dependencies that you might have. So that's also one of the use case, and of course this is a small diagram that you can see that we might have like multiple WASM functions, and they can directly be used by the developers in order to deploy and manage without having to worry too much about the dependencies on or be constrained because of the platform in which they are actually running these WebAssembly functions. And here is a quick demonstration. Of course, since we are limited on time, we could not show the demonstration, but we have already covered a WebAssembly based function as a service where you're actually running again a machine learning inference on the edge using WebAssembly, and that's specifically using WasmEdge. So if you are interested to kind of see how we built that, you can see the demonstration for the GitHub link, and also a video where we basically covered this at a Linux Foundation event itself. So I'll recommend you to check this out in case you're interested to kind of see how you can run these functions on the edge specifically. And then I just want to cover one last point, and that's basically the smart devices. So as we mentioned that the WebAssembly runtime, that's WasmEdge, can basically run on multiple platforms. So in case you are working on Edge specifically, and you might be working with hardwares or OS such as OpenHarmony, Raspberry Pis, or even RTOS, then basically WasmEdge can run your WebAssembly applications on these specialized hardware as well, which allow you to run very easy inference. And again, of course, our angle was to showcase machine learning capabilities, but if you are not into machine learning and you have any other highly compute intensive tasks, you can use WasmEdge to run on so many different type of devices as well. And here's the benchmark that Rishit will be talking about.
So this is the benchmark for the exact same application, and I will end with this. And so we just wanted to show WasmEdge versus TensorFlow Python in a Linux container. And so this is TensorFlow Lite. We were compiling to TensorFlow Lite and then using WASM to run TensorFlow Lite. And I particularly want to show WasmEdge with AOT compilation. So a lot of speed of WASM also comes from AOT compilation. And these are benchmarks on the exact same model we were showing the demos with. There's also some code to produce these benchmarks. But yeah, this is a quick benchmark for the task the task at hand. With that, we come to the end of our talk. Thank you.
And if you have any questions, please.
So with the WASM being bytecode, is there a CPU penalty that you need to pay when you run this versus a container that's running a natively compiled application, for example?
So, okay. As far as I know, there is no CPU penalty you have to pay, and that's just because running WASM in, let's say, a container is pretty straightforward as well. You just create a container runtime which will have no guest OS, and it boots up faster, and it runs faster than the same process written in a Linux container. So as far as we have observed, there is no CPU penalty in terms of the resources used, as well as the size. But
Size, I agree that there is a benefit. How about a natively compiled application, like no container, but you have a binary that's running? Is there a data or something about that?
Yes. So one particular thing, it's a bit slower than natively. Then you directly make a binary and then use it. It's a bit slower than that. AOT compilation can solve that. AOT compilation does solve that. But one of the things I also wanted to say, having said that, just using WASM is slower than native compilation. And pair it up with AOT compilation, you get to the same speeds. But I also want to say there is still use for just WASM without AOT compilation, which is portability on multiple devices. So if there are no more questions, we come to the end of our talk, and you can always reach out to us on Twitter if you have questions in future.
And if anyone is interested probably to stay back and see the Woggy demo, we can probably showcase that. And by the way, we have a few stickers from the WasmEdge runtime. If anyone is interested, you can pick them up.